Welcome to the sixth presentation in the fourth webinar series presented by the International Adsorption Society. The IAS is an international organization dedicated to advancing adsorption as a solution to scientific, engineering, and human welfare challenges through the promotion of adsorption research and education. We thank everyone for attending the webinar today. The webinar series has been an immense success, and the recordings of previous webinars continue to be viewed on YouTube and Bilibili. This is the sixth webinar of our fourth series, which we will continue to have monthly throughout the year. We intend to continue with a variety of speakers from industry, academia, and other research institutes, as well as PhD students and early career researchers. Announcements regarding the fourth series will be distributed through the IAS mailing list and the IAS Twitter feed. Today's webinar will be given by Professor Carlos Grande at the King Abdullah University of Science and Technology in Saudi Arabia. I'm Nicholas Wilkins at Sfonte Technologies Incorporated. Today's webinar will be moderated by Bhupesh Murugapan at the University of Alberta. We are required to remind attendees and future viewers that the views expressed by the speaker, host, or other moderators are not necessarily those of the IAS or the institutions associated with those individuals. We ask that you consider joining the IAS as a regular member if you are not already. Our dues are minimal, only $20 US per year, but support the publication of our flagship journal. Adsorption, contribute to travel grants and workshop seed funding for IAS members and affiliated groups, as well as aid the organization of our triennial conference on the fundamentals of adsorption. Members also receive free access to IAS supported materials, including our journal, as well as the adsorption database published by Springer Materials. Anyone can follow the IAS on Twitter at @adssoc for future updates regarding IAS events, webinars, and information about scientific meetings. Please help us expand our YouTube channel by liking this video and subscribing. I'll now hand it over to Bhupesh, who will moderate the YouTube Q&A.
Thanks, Nick. It is my pleasure to welcome Professor Carlos Grande to today's webinar session. Professor Carlos Grande has been an associate professor at KAUST since September 2021. He leads the Laboratory of Intensification of Materials and Processes and is affiliated to the AM, PM, and KCC centers. He finished his undergraduate degree in chemical engineering at the National University of the South in Argentina in 1998. He then went to Porto, Portugal to do his PhD at Porto University. He completed his PhD in 2005. Afterwards, he worked at Porto University for 5 years as a research assistant. Before joining KAUST, he worked as a senior scientist in Sintef Industry for 10 years in Oslo, Norway. He is currently a member of the board of directors of the International Adsorption Society. He works with process intensification applied to separation and reaction processes with strong focus on adsorption and novel manufacturing techniques like 3D printing. He has over 120 publications in international journals with an H-index of 48 and 7 patent applications. During the webinar, questions can be submitted to the speaker as comments on the YouTube live stream. Questions will be answered at the end of the presentation. With that, I welcome Professor Carlos Grande again and pass over the presentation to him.
Thank you very much, guys. So can you hear me now? I will share my presentation.
We're able to hear you, but we're just waiting on you to share. Excellent. Yeah. Yep.
Good. So thank you very much. Thank you very much for this introduction, the kind introduction and the presentation. I also want to thank you guys for taking this initiative of making these webinars. I think this is a very useful service that you're making to the Adsorption Society. And this is something that is very interesting. So as you heard, my name is Carlos Grande. I'm in KAUST for almost the last 2 years. Our lab has a distinct particularity. We belong to 2 centers, the Advanced Membranes and Porous Materials, where we basically canalize all our adsorption part, and the Catalysis Center, where we work mostly with 3D printing. And today we will be talking about pressure swing adsorption for biogas upgrading. A little bit of This is not really moving. Yes, a little bit of a graphical introduction of what you just mentioned before. Let me put the pointer here. So I was born in Argentina and I studied chemical engineering in the South University. And after that, I moved to Porto to make a PhD, 2005. Then I kept on working on Professor Alirio Rodriguez's lab for 5 more years as an assistant researcher. Then I moved to Norway. And in 2013, I became a senior scientist because I got a big project together with Australia. And at that time, in 2016, I had the opportunity to take a mini sabbatical term at the University of Melbourne with the Paul Webley's group, which I'm very, very happy that I did that. We fell in love with Melbourne. And then after coming back in 2021, I finally moved to Saudi Arabia to become an associate professor of chemical engineering. As many of us as researchers have to move around the globe, as I had to do, some of us experience some changes, not just in culture, not just in things, but also in weather. This has been so far one of the most challenging things that I have experienced moving from Norway to Jeddah. The weather difference here, when we are supposedly comfortable, we used to be freezing, and yeah, that puts some constraints on the body that needs to be attended for. But yeah, it's something that we are managing rather well. Another thing that normally happens is that when we go to conferences, particularly the fundamentals of adsorption, we go alone and we don't show you the people that makes us happy every day, right? So I want to take this opportunity to show this. She's my wife. She was born in Poland. Gosia has a PhD in chemistry and used to work in GE Healthcare before she started working in KAUST. My daughter Eugenia, she's 22, so 23. She was born in Portugal, and she's a master's student at the University of Oslo in Norway. So Ragnar and David were both born in Norway. Ragnar is now 7. He finished his first year in primary school, and David here is showing you one of the fantastic sunsets we have in KAUST. And this will be his last year of a kindergarten. So after this short presentation, I'll start working on explaining you why we started working with biogas. It's obviously within the context of climate change. We normally hear a lot about carbon dioxide accumulation in our atmosphere, but we rarely hear that methane is also accumulating in our atmosphere very much. And since the greenhouse warming potential of methane is much higher than carbon dioxide, when we look at the cumulative emissions of these gas of non-CO2 emissions, they actually play a big part of accumulation of greenhouse gases in the atmosphere. When we look at the IPCC mitigation options to tackle climate change, we see basically a battery of possibilities to reduce greenhouse gas emissions. And I hope that after the first introduction, I can focus on which ones we can tackle by biogas. So let me show you what is biogas. Actually, biogas is the gaseous product of bacterial decomposition of organic matter in the absence of oxygen. So methanogenic bacteria start working particularly on fatty acids, and after you manage to get this in the absence of oxygen, which is very important, you can get a mixture that is majoritarily composed by methane and carbon dioxide. Some common streams that are found in industry, that are found around the world, has around something like 30 or 40% of carbon dioxide, with a large content of methane, of course, and they can have some sort of minor components, which are not sometimes so minor. In this case, is hydrogen sulfide. When we're talking about sewage plants, we have also a percentage of methane that is between 55 and 65% balanced by CO2, which is still quite much. Not too much nitrogen, not too much hydrogen sulfide. And when we go to landfill, we have a serious amount of CO2 between 30 and 40%. We can also have a lot of nitrogen depending on how the landfill gas was extracted. If there is, let's say, extracted at a higher rate, some oxygen from air managed to squeeze through the landfill and pops up together with the biogas. So as you could see, the different types of organic matter can be sort of accumulated here, and then they are routed to a primary digester and a secondary digester eventually. And from there, you can extract the biogas that you're going to use for the different purposes. If that was the only situation in the world, that would be okay, or more or less okay. But the problem is that still in a lot of places, this is not yet done. There are a lot of places where actually the rubbish management or the wastewater treatment plants are sort of open sky. So you can see, for example, in this picture, after 2 or 3 layers of rubbish, there is basically no oxygen, and the methanogenic bacteria is able to do their jobs. So actually methane is being constantly released to atmosphere. So we are emitting methane with these activities. And this is something that we can try to fix. The other question is where we can produce biogas. I mean, biogas, as you have seen, is a lot of methane. So methane is sort of, in the mind of a lot of people, is compatible with natural gas. And there are a lot of countries that do not have natural gas. But that doesn't happen to methane. We can produce biogas in all of these countries. And actually, there is no geographical limitation for that. And it's mostly associated to efficient handling of human activities. As I explained before, if you treat your rubbish well, if you treat your wastewater well, you are able to collect biogas. Now, for that sense, I'll just show you 2 pictures. One of them is actually written in Norwegian, but it's talking about the utilization of biogas here in these islands in Svalbard. There is very little amount of people living there, but from 2023, the airport is going to be run on biogas. So it's showing that it's possible to take advantage of this resource very close to the North Pole. So temperature has proved that it's not a big limitation. And another example here is in Costa Rica, where there is actually a biogas association. Again, with very little resources, and eventually doing this in small farms. So also showing that when people has a will, there is a possibility to exploit this resource in a profitable manner. So, as I was showing you before, you have organic matter, you put it in an anaerobic digester. So far, we have been focusing on the biogas, but we also have to remember that we obtain from this digester a digestate that can be used as a sort of organic fertilizer for soil amendment. And this can also contribute to climate change. But focusing again on biogas, the things that we can do is use basically burning it to produce heat, eventually to produce electricity, or we can upgrade it to obtain biomethane. And this is what we're going to focus today, so that we can use it in a fuel or eventually inject it in a gas grid. So we can inject, in many countries it's allowed actually to inject biomethane into the existing natural gas grids, so that it can be this renewable energy can be used remotely. So with one single source of gases, you can produce heat, electricity, fuel, or inject it in the gas grids. So coming back to this battery of options for climate change, you can see that with biogas, you can produce bioelectricity, you can produce biofuels for transportation. If you start using more biogas, you can contribute to fuel switching. There will be more cars eventually available to use this biofuel, or to use this energy remotely if you inject it in the natural gas grid. And you obviously contribute to reducing methane from the waste and wastewater. I still don't understand why in the last IPCC report there is not a single mention to biogas, but maybe it's something that is understood by all the parts. But I think it will be interesting to see that this word is present in there. Another advantage is that if you already have a bus fleet that is running on natural gas, adapting this to using biogas, which is a completely renewable fuel, will basically cost you zero. You can see that in the natural gas and biogas buses, the tanks are here on the ceiling. If you want to make some numbers, these are several cylinders that are stored here. with a capacity of 220 cubic meters at the pressure of 200 bars, given a driving range that depends on a lot of factors, but it can be between 300 and 350 kilometers. So how we do this, how we upgrade biogas to biomethane? As shown before, there are some components that we need to remove. In the list, in that simplified list that I show, there was a lot of H2S in some of the components. We need to remove that. If you're working on a silo and on the biogas from landfills, you might have siloxanes, you might have ammonia, you might have a lot of different components that you would like to remove before moving forward. Also, if you're going to use adsorption here as a technology, and most of the times also if you're using membranes, the next thing that you're going to do is to remove the water. Biogas, when it's produced, is normally produced with 100% relative humidity, so it's saturated in water, and you want to remove this water. Normally it can be done by some membranes or by TSA. And finally, you end up with a binary, a mixture of methane and CO2. And I remember that this is a bulk separation, since you have at least 30-35% of CO2 to be removed. So at the end, you obtain your biomethane as a product. If you put a little bit more of effort, not too much, a little bit more of effort, you can also obtain CO2, very concentrated. So if you have a very large source of biogas, you can even get yourself the luxury to get the CO2 that you can use for CCS. In terms of pressure, operational pressures, you have a biogas that is, I would say, normally delivered at 1 bar. Can be a little bit higher, but normally for some accountabilities, you'd say that it's delivered at 1 bar. And these processes are normally run between 1 and 10 bar, considering that you will have to remove a large fraction of CO2. It's not really worth it to compress the whole thing to 250 bars, which is what you require to fill up the tanks, or sometimes around 200 bars to inject it into a natural gas grid at high pressure. Also, when you have the specifications of this, we say that we want biomethane, but we didn't put any specifications. So the normal specifications are related to something that is called pipeline quality biomethane, pipeline quality methane, which implies that the dew point is minus 50 degrees C, so it's quite dry. The amount of CO2 depends on the country, depends on the local legislation. There are countries that put the cap in 2%. There are other countries that put the cap in 3.5%. We just rounded up to 2.5%, but remember that this depends on where you are. And in the case when you have nitrogen in the biogas, this nitrogen will probably pass through a lot of different stages. So you also have a cap of 4% of inerts that you cannot have in this natural gas. So remember, the dew point is very low, so there's very little water, there's very little of CO2, and this is due to is trying to avoid corrosion in pipelines and in further equipment to treat this. But I want to focus particularly on this part that is a very dry product. And sometimes what I see in literature in adsorption liquid, in adsorption papers, is that sometimes a lot of people is saying that some particular materials cannot be used because they are not tolerant to water. But as you see, in this stage, we already dried our gas quite much. So I don't think that this is entirely true. I think that if the material is good enough, and we are very happy with it, as long as it's well packed inside the PSA, which is normally the case, these materials can be used for biogas upgrade. Another thing that I didn't mention, but you can see it here, is that there are very different projects, there are very different technologies that can be used for natural gas upgrading. In this particular case, sorry for this, but this is the best graph I could find, and I didn't want to change it, but it's pretty understandable. It's in Swedish. Is raw gas capacity. So this is the amount of biogas that you're going to treat. And there's a curve here that is telling you how much is going to be your specific investment cost to apply one of the upgrading technologies in euros per cubic meter per hour, right? So one of the important things is that, of course, that these curves depend on a lot of factors. you can see that there's not too much of a variation. Some of the processes are more studied, so they have a better curve. But one overall tendency is actually that when you go down to small applications, the cost increases exponentially. And this is something that we will be talking about a little bit further, right? So the question here is how we can reduce the cost of installing such a unit, such a biogas upgrading unit. A lot of people is not available to pay for this, and we have to focus on delivering a good technology as cheap as possible. Before I say everything related to biogas, I want to make a point. I mean, now the world is a little bit different from what it used to be when I was a PhD student. But 20 years ago, I finished measuring a lot of data of adsorption equilibrium, a lot of data of adsorption kinetics. So it was time to read some things about pressure swing adsorption. Finding papers on the internet was not as easy as it is today. So there was a traditional way of doing that, which was basically go to the library and read. And the Adsorption Journal has been an important source of information from a lot of time. And right in 2002, so let's say 21 years from now, I just went to look for PSA papers and I found this: landfill gas from rubbish to resource. At that time, I had to recognize I didn't even know what it was, a landfill gas. So I read this manuscript. I think this is probably one of the best manuscripts I ever read in my entire life. So I have to thank Kent Nagel for writing this. I started thinking about working in this topic from that moment on. This manuscript has very few references, and one of the few references that it has is a paper from Professor Seeker, working on this topic of methane and CO2 separation, and this publication is from 1988. Okay, so we're talking about research that has been done for a very long period of time. So when we think that research started quite early, the explanation or the question arises immediately is why it started so early and why it continues now? And the answer is quite simple. This is profitable purpose. So this is something that we have to keep in mind. So now going to the explanation of a pressure swing adsorption. For a lot of people, pressure swing adsorption is a technology that is not commonly known, but we can try to explain it in a simple manner. It's a discontinuous system composed by multiple columns loaded with an adsorbent. When one of these columns is processing the feed stream, the other column is being regenerated. And we do that so that we try to mimic a continuous process. So we put more than one column so that for the rest of the units, the PSA will operate as a continuous process. So you pass a feed for a certain amount of time, you adsorb. In this case, you're adsorbing CO2 across the column. And before it breaks through, before it exits the column, you just switch this column out from the system and start passing the feed through the other column, and you start regenerating this column. So your feed is at a higher pressure and your regeneration is at a lower pressure. So you're actually reducing the amount of CO2 so you're in the column, so you're dissolving it from the material, and with that, you are able to run it again at high pressure. So this is what you're going to do in the different cycles. Obviously, this is an ideal situation when your PSA is isothermal. This is rarely the case. In this particular case, you're talking about bulk separation, so there will be a lot of energy released with CO2 adsorption, with CO2 desorption. So this will be sort of having a very ideal PSA, but it's probably not going to happen. Also, explaining a continuous PSA with a two-column system like this is not possible, because for energy optimization, there is a step called pressure equalization. And in that fraction of time, we are taking these two columns actually outside of a system. So to make this process continuous, we have to fix a tank at the beginning, right? This is the simplest way to try to explain a PSA. If you want me to show you a fully continuous system, we have to put a little bit more of columns so that you see that the adsorption is always continuous. So we are always processing biogas, in this case, first to column 1, then to column 4, then to column 2, then to column 3. And so we keep on doing this for a lot of cycles. This is a commercial unit for biogas upgrading. There are several companies that are providing this, a very non-extensive list, and I have to highlight this, a very non-extensive list is displayed here. I just selected these companies for a lot of reasons. Carbotech is using material called carbon molecular sieve, and you will hear about this material a little bit more. EcoSpray is doing this with the modified zeolites, and Guild Associates in the United States is using a very interesting material. It's a titanosilicate, which was under secrecy for a lot of years, and unfortunately I could never have a single pellet in my hands to make some tests. And CIS Advanced is a company that was generated by some people that was making PhD at the same time as I was doing this. They are in Porto, and actually I'm streaming this webinar from Porto, so this is why I'm putting them in here. So what we expect when we are operating a PSA? So we pack the adsorbent material through a column, we start passing biogas here. And what we are expecting is that methane adsorbs, like methane exits the column very fast here. So it exits the column very fast. You can see this in the outlet, in the breakthrough curve. And for a certain period of time, you can get methane free of CO2. And only after a certain time, when your adsorbent is saturated, you can start seeing CO2. So for this window of time, you will have a feed that is going to be purified methane. How you can do that? What kind of adsorbents you need to do that? So you have two opportunities. The first one is that methane is very slightly adsorbed. So in this particular case, remember you have more than 50–60% of your stream that is methane, and it has to be very slightly adsorbed through here. And this is what we know as equilibrium adsorbents, or we have another option. Since methane is a little bit larger than CO2, we have some particular materials that have very narrow pores, and in those materials we can make a trick. We can make methane to be able to penetrate into those pores very, very, very slowly. And as you're putting this in contact for a very small amount of seconds, there is no choice that it will have to be adsorbed, so it actually exits the column very fast. So this kind of materials, the separation is driven by equilibrium, the isotherms, and in here the separation is driven by diffusion. Since this is less common, I will focus more on the talk today on this particular case. I made this animation a lot of years ago, and this is sort of a slit pore from a carbon, and you generate a carbon molecular sieve by carbon vapor deposition. So you put a little bit more of carbon at the mouth of the micropore, as it's called, and you do it in such a way so that the CO2 can penetrate rather easy into this structure, but that methane has a lot of difficulties to penetrate in there. So I'm not saying that methane will not go in, but methane will have a lot more difficulties to go into that structure. So what happens when you measure isotherms? You see that indeed this is a carbonaceous material, so methane and CO2 adsorb. The selectivity is not that high in terms of equilibrium. You don't have a very, very little amount of methane adsorbed here, but the difference is achieved in the selectivity. Please note that here the time is expressed in square root of time. So let's say to reach equilibrium in the first point of this adsorption isotherm, CO2 took around 350–400 seconds, and at this time there was very little amount of methane that could be adsorbed in that material. So this is how you achieve separation, not by equilibrium, but on the difference of adsorption rates. I also have to make a point on this on this data. As you could see here in the isotherms, there are very little points in these isotherms, right? I want to reach that because it's very difficult to measure those isotherms. Each of these points take at least a couple of days to reach equilibrium. So if you want to measure an isotherms with around 10 points, your measurement will have to stay there closed very tightly for at least 1 month. And a very, very small leak, and I'm talking here about a very small leak, will be understood as adsorption. So your system has to be very well tuned to be able to measure this data. Again, once you reach the ISO 10, if you're very interested in measure how the desorption is taking place, you have to remember that if adsorption takes 2 days, the desorption will also take a little bit longer. So in that case, you have to be prepared for a longer, very long measurement. I'm trying to explain here how we do it. Normally, a lot of equipments that are commercial are fixing the interval of pressure that you have to give. And what you can control is the amount of time that has to be maintained below this pressure. I remember when we measured this in my previous institution in Sintef, we used to have a Adsorption Max. Was not one of the newest versions, and our limitation was actually 9,999 seconds. So if you look at this curve and you see our equilibrium value was, let's say, around 2-3 days, and it was at 2.1 kilopascals. So the final part is very, very difficult to determine. After you measure this, what you do is you pack your carbon molecular sieve in a column. In this case, we were having columns of 56 centimeters long, and you measure breakthrough curves. So for a certain period of time, you will see that methane goes up very fast. Before measuring the breakthrough curve, we pass some helium, and at time 0, we just switch the helium to biogas. Methane exits the column super fast because it's not adsorbed in this carbon molecular sieve, and for a very good period of time, here around 12-13 minutes, you have a pure stream of methane exiting. Breakthrough of CO2 starts happening afterwards. One important thing when you report this kind of breakthrough curves is not just to report the molar fraction or the molar flow rate or something, but also to report what is the temperature that you are obtaining in the column. If possible, to measure the temperature in different places around the column, that helps a lot. In this case, we can see what is CO2 at a certain time within the column just by looking at the thermal profile. Also note that there's only one peak, so no matter what is the heat of adsorption of methane, since there is very little amount of methane adsorbed, there is no really a peak of methane that we can see here. When we have all these parameters, we can just feed a model, and with our model, we can predict what is the performance that we're going to have in a PSA. So in this system that we had 4 columns, we start by a very simple system of using 2 columns. And you can see that for a certain amount of time during the feed step, you basically produce pure methane, very little amount of CO2. And when you're doing regeneration, you obtain the CO2 with some of the methane that was in the column. And with this kind of 2-column arrangement, we only have one pressure equalization. So for that reason, we are always going to have a little bit of methane unless we do other steps. But with this simplified arrangement, we are only going to have a little bit of methane exiting here. And the same, let's say the mirror image you will see in column 2. When this one enters into regeneration, the other column is producing methane. And when this one enters into regeneration, you produce CO2, concentrated CO2 stream. In this particular case, we were cycling the pressure between 5 bars and 0.1, 0.15, if I don't remember that. That was what was used. But regarding this, I want to try to talk a little bit about the social aspect of this. Imagine that I show you a world map where the countries are not having the shape that they are having by now, but that the shape is proportional to the population that lives in that particular country, which is very curious because in some countries like Canada, it becomes very flat. Scandinavia becomes super small, same as Australia. And like a lot of countries become much larger than what they really are, right? So when we correlate this image with the GDP, these countries, what we start seeing is that a lot of investment that has been done on biogas upgrading has been done in the countries that are painted green. which are the countries that are very small in here in terms of population. So if we really want to make a big impact in terms of climate change, that is a global problem, what we actually have to start thinking is about how we're going to design PSA units for biogas upgrading that can be used in these countries that are not really painted in green. And this has been the driving of our research for many, many years. So for that, I will start showing what we did in different possibilities, how we're going to do that for low GDP countries. And the reason is kind of graphically obvious. You see a biogas production plant in a developed country, and all the facilities are used. This water treatment is closed, so the biogas is being collected, and you put in a grading module, and it more or less fits here. So if you, let's assume if you have a gas capacity of around 1,000 cubic meters with any of the processes that you put here, you have to be ready to pay around 2 million euros for installing that biogas upgrading plant. Okay. But now you look at this gentleman that is in this picture, that is posing for this picture very proudly, and he has reasons to be proud because this guy is very, very renewable. He has a biogas container on top of his house. So he's using this resource very efficiently. He's using this for cooking, eventually for warming up in cold days. And we have to start thinking that eventually one day he can increase his property and eventually need a tractor or need some sort of mobility. And with this biogas, he can obtain the fuel that he needs for reducing his manual labor. And eventually that will be very interesting. But of course, if we come back to this part, even if this gentleman has a very small capacity, he's certainly not having 500,000 to put on a PSA for biogas upgrading. So this is one of the reasons why we work on PSA. When we look at all these different technologies, most of these are scrubbing technologies with water, with the mines, with another particular solvent. We see that they are not very flexible in terms of technology. You will have an absorption tower, you will have a regeneration tower, and depending on the particular conditions, you will eventually reduce the size, but you will not go farther from there. The same is with the membranes. You will have a certain selectivity for your membrane that will make it be a little bit smaller, a little bit larger, a little bit more power consumption, but it will not run very differently from there. With the same thinking, we can have comparison with materials. If we use only one material, let's say carbon molecular sieve, and we want to scale our process down, we're also going to have a similar situation. However, the fantastic thing about pressure swing adsorption is that it's a very flexible technique. And as I was showing you before, we can either use 2 columns, 3 columns, 4 columns, eventually 6 columns. And the process, the process configuration changes dramatically. So we can eventually produce by PSA something that can reduce these costs dramatically in this particular region. And eventually does not make any sense if it's scaled up, but that doesn't really matter because there is a lot of users that could benefit if we can scale this down to this region. Okay, this is like the real motivation where we only focus on PSA. So one of the first things that we did was actually to focus on cheap adsorbents. There is probably nothing cheaper than silica gel. So with silica gel, the selectivity of CO2 towards methane is not really that high, but obviously it's silica gel, right? So it absorbs a lot of water. And as you heard before, biogas is saturated with water. So in this particular case, what we were looking at is to combine 2 different steps, the water dehydration and the CO2 removal. So instead of having 3 large steps like the guard bed, the water removal and the CO2 removal, you can only have 2 steps. So you are not going to remove water by TSA or by membranes, you're going to remove it together with CO2. We made some breakthrough curve measurements just on the dry system. And I have to say, the system will eventually work, but the larger problem is indeed the lack of selectivity. So there is a lot of methane that is absorbed here. So The breakthrough is not as fast as we were expecting. It's taking a lot more time. So we will have some issues with the methane recovery. We will have some methane sleep. In the case of developed countries with a lot of legislation about the possible methane sleep in the product, we might not reach that specification. At least with a simple cycle, we have to make large cycles, and that will only be suitable eventually for large scale applications and not really for small scale applications. After that, we just made a very simple cost analysis. So we started with 3 different scenarios that I will explain later. So it's 2 columns and a tank, 3 columns and a tank, and 6 columns. So with all these possibilities of PSA, we could reach methane purity as a side and a very high methane recovery. So we put 3 different scenarios, completely random, like what will happen if we have an adsorbent that is 5 times more than a commercial, which is basically carbon molecular sieve. And the third scenario that I will present here is what will happen if we have like all the infrastructure, the columns and the valves that are much more expensive than what they are. And the conclusions are quite easy. So when the adsorbent is very expensive, you will obviously be dominated by the cost of the adsorbent. But in that particular case, what is interesting to highlight here is that you will prefer to have systems that are much more efficient in terms of performance. So you will prefer to have a 6-column system, right? Well, when the infrastructure is more expensive, that doesn't happen, and you will prefer to have simple systems, and the cost of your adsorbent is not going to change dramatically. So this means also that there is a lot of possibilities to use some materials that are maybe not the cheapest ones in small applications, but to focus on very simplified production schemes. Obviously, I have to highlight again, this cost analysis is only valid for downscale systems. If you're going to think about a very high flow rate treatment with a PSA, like the infrastructure will dominate the cost completely. And also note that here I'm not talking about a vacuum pump or a compressor, because they're going to be common in both of these applications. So one of the systems that was analyzed here is 2 columns and a tank. And why we did that? Because with just 2 columns, as I explained before, we had a dead period here. But if we make the pressure equalizations from 1 column to a tank and from this tank to the column, we can actually transform this into a continuous cycle. And there we don't need a larger tank here. We just need a small tank in between the columns that will compensate for this time. Also, the amount of valves is basically untouched or only increased by 1 at the maximum, just for safety reasons. So we have the less equipment as possible. But unfortunately, as we only have 1 pressure equalization, we will have some methane sleep. And this is something that in some countries will not be accepted. So if we want to reduce the methane sleep with this configuration, we have some issues. So we have to go into a little bit more columns. So the only reason to have 3 columns here is to have more than 1 pressure equalization. So when you're ready to dissolve the CO2 from here, the partial pressure of CO2 is very high. So you don't have basically methane, and your purity is very high. And also, instead of putting a 4th column here, we just have a very small tank that is smaller than the columns, or a little bit smaller than the columns, and only 1 valve. So if the valves are an issue in very scaled down processes, we are reducing that quite significantly. So some final remarks. Biogas upgrading to biomethane by PSA is a commercial level. It's a state-of-the-art technology. We can use several adsorbents. As you noted, I didn't really focus too much on the material. As I mentioned before, there are people using zeolites, there's people using carbon molecular sieve, people using ETS4. We even tried with silica gel, and we sort of proved that it can work. So materials is not a problem. And the cost of the adsorbent might not be the main limitation, at least to deploy new units. In the large scales, if you're operating in a large city and you have a wastewater treatment, possibly recovering biomethane, you can also think that with that, you are also going to have a very concentrated source of CO2. If you're interested in CCS, that's a good possibility. And the most important thing here, I hope I could highlight that, is that PSA units are offering a very large design flexibility, and we need to explore a little bit more how to scale down the systems to be cost efficient, particularly for low GDP countries. So PSA for biomethane production is a climate-friendly technology. Now that we're talking about circularity, this is helping us to treat our rubbish in a sustainable way, and most importantly, is quite profitable. So with this, I thank all the people that was working with me in this task: master students, PhD students, colleagues, researchers, technicians, everybody that helped me to work on this for the last 20 years in Porto University, in SINTEF, now in KAUST. I put here a list of the people that was in the last project that we had when I was in SINTEF. Andreas Kaiser was handling this project from the Technical University in Denmark. I learned a lot in that project. This is the main project where we actually focus on scaling it down. Finally, I want to say two things about this picture. This is a partial picture of our group. Not all the people was able to be here. But again, as I started with a lot of mobility in the research arena, I want to tell people, please, if you're making a PhD, if you're making a postdoc, and try to learn the good things from the place that you're in and try to transplant them in the next place where you're going to go. I think that this makes the research arena a lot more culturally rich. So this is not just that the guys were posing for the picture with a lab coat. This is something that I learned in SINTEF. We call it Dugnar. And this is the day where we basically clean the lab, and at the end we eat pizza. The third thing that I want to highlight in this picture is this gentleman here in the back. So a series of results that I presented today were taken by Rafael. Rafael was a PhD student in Brazil, and he visited us for 1 year when I was in SINTEF. He did a fantastic job in there, and I'm very happy that he accepted the position of being a researcher in our group. So with that, I think I've finished, and I want to thank you very much for your attention, and I hope I can answer your questions.
Yeah. Thanks a lot, Professor Grande, for your talk on biogas upgrading. We can now appreciate the need for both sorbent and process developments in this field. We do have a couple of questions from YouTube. One question is from Shubhra Badra. Their question is, for any of the solutions that you had mentioned, can you handle H2S?
So H2S is going to be eventually removed. I mean, we didn't study H2S too much. You have to have a very dedicated lab to do that. There are a lot of different possibilities of handling H2S, including recycling, or eventually some people is just throwing some steel lime into the biodigesters and reducing the amount of H2S much. But no, I didn't focus on H2S. That's a particular area.
Okay, yeah. While we wait for more questions, Nick and I have a couple of questions for you. So in the initial schematic, it's shown that we have a guard bed, a drying unit, and the biogas upgrading unit. So do you have any idea about how much would the drying unit contribute to the overall cost? Because usually people think drying is expensive. So.
Yeah, but here, the flows are normally, let's say, 2, 3, 4%, depending on the temperature that you have. So the contribution depends on a lot of factors, and particularly on the pressure that you're operating your system, right? So if you have, when I say that you have 3% of water, for example, when you start compressing, you can knock down a large amount of water. So you can even give yourself the luxury of integrating the water into the PSA. And that's what a lot of people started doing nowadays. So the cost is sort of hidden in the cost of biogas, in the cost of upgrading, in the cost of CO2 removal. So it's not the same as removing water from a flue gas.
Okay, yeah, makes sense. There's a question from Kian Karimi. Their question is it possible to separate very dilute methane in the range of ppms from a nitrogen mixture with carbon molecular sieves?
I didn't try. There's a lot of interest in that. Actually, there are some old publications also that were focusing on that aspect. There is something that is called coal bed methane in several countries, but also nowadays in some countries, again in developed countries, people is thinking about this in the context of like cows, for example. So no, I didn't try that, but also remember, is if it's only methane and nitrogen, it should be doable. But if there are other components, oxygen and water, it's a bit more complicated, and CO2.
Okay. There's one question from Alexandra Marcinek. The question is, does the PSA pilot plan for the biogas upgrading need to be designed according to the ATEX certification?
Yes. Yes, that is actually one of the things that contributes to the cost quite much. So it has to be ATEX or ATEX 2, and this contributes to the cost a lot. Thank you for the question, Alexander. Nice to hear from you.
Yeah, there's one more question from Diego. In case we also want to obtain pure CO2, how much would that add to the overall cost? Would the investment cost increase?
Sure. In some countries, actually, is the methane sleep in Scandinavia, for example, the methane sleep that is allowed is very low. So you have 99 plus of CO2. I don't know how much people want to obtain. I know that there is one place, at least in Denmark, where they are obtaining CO2 with food grade. So it's very high purity. But for that, they have to put an additional process.
Okay. There's a question, Alexandra Marcinek has one more question. Are variations in the feed stream composition generally considered while operating the plant?
We were not operating a plant. We were designing PSA, so we didn't do that. But indeed, here this is a significant issue. The variation of the flow, the variation of the composition. If you're thinking about a landfill gas, the variation of the composition can change dramatically. And so one day you might have a lot of CO2, and the other day you might have a lot of methane. So this poses a lot of issues regarding the control of the PSA. So this is something that we didn't focus yet. We started looking at that, but we didn't really look at that much. But this is a very interesting area indeed.
Okay, and there's a question from Gopeng who the question is based on we have a tiny amount of nitrogen in the biogas. How do you usually handle that?
Well, nitrogen gets a little bit more absorbed than methane, but not that much. So at least in carbon molecular sieves, the nitrogen indeed, if you're limiting that into 4%, is the nitrogen that is going to regulate that. You start feeding a ternary mixture, which is methane, CO2, and nitrogen. And when you reach basically the 4% of inerts that you have to shut down the feed and put the column for regeneration.
Okay, and will make sense. There's a question from Carsten Vion on YouTube. Can you elaborate a bit on which adsorbents are most promising ones? And do you also know of any adsorbent screening performed regarding their efficiency?
Can you repeat?
So their question is, which adsorbents are most promising? And do you also know of any adsorbent screening studies that have been done for biogas upgrading?
Okay, so differently from a lot of other applications that are at the research level, this is a commercial application already. So the most promising are the ones that people is using in industry. So it's carbon molecular sieves, titanosylicates, titanosylicate 4, ETS4, in the case of guild associates, and some modified zeolites. So if you ask me if there are more promising materials, yes, there are. You have to try to look at kinetic separations or materials that absorb very, very little methane and absorb more CO2. There are a couple of them. I don't know. I actually don't read reviews. I don't like reviews. Sorry, this is a personal opinion.
Okay. One final question from Nick Wilkins. What is a good approach to design adsorptive processes involving slow kinetics? How does the slow adsorption of methane affect the process design?
Yeah, well, the slow absorption of methane is actually what dominates here. So you have to be sure that your methane adsorb, and we're talking about in terms of LDF coefficients around -5. So what you have to do is try to, let's say, get the column absorbing, I would say, up to 60-70% of the total length of the volume in terms of CO2, and then just start from there. So you have to have a good model and start optimizing.
Okay. Yeah, we do have a couple of questions on YouTube. 2 more questions. Would you like taking them? So there's a question from Pedro Augusto Mora. Regarding cost, what is the biggest drawback in biogas upgrading? Is it the adsorbent capacity, or is it because of impurities?
The bigger cost of the PSA as it's designed today is actually the vessels, the steel that you're using. As we were asked today, a very large amount of the real cost on putting this up and running in a place is that you have to design it as ITAX. So this puts a lot of cost in the entire system. So if we can start thinking about making smarter designs that can reduce that cost, so that you only focus on ATEX where it's really, really necessary and not all around, you might get some cost reductions.
Okay, makes sense. There's one question from Abdullah. How do you compare using PSA versus amine absorption for natural gas purification?
I didn't compare with we are better. No, I didn't make that comparison, but it also depends on a lot of different reasons. You have to think that, for example, if you're working with a landfill gas where you might have oxygen in there, you would not like too much to have an amine in there. The same if you have a certain amount of nitrogen. With the amines, you will not be able to treat the nitrogen at all. So as I mentioned before, the carbon molecular sieves will partially absorb the nitrogen and will help you with the final specifications. Regarding the amines, I mean, if you're using a carbon molecular sieve, it's basically an adsorbent that, well, if you want, you can eat it. Amines are very toxic.
Okay. There's one question from Alexandra Marcinek. What are the implications of co-diffusion in a binary mixture of methane and CO2 in case of separation on carbon molecular sieves?
What do you mean, what are the implications? I mean, you get separation.
True. Yeah, maybe we'll wait if they clarify the question, but yeah, I don't see any other questions right now. So
the implication, I mean, I might answer. I got a couple of questions like that before. What people was meaning is like, of course, if methane is, if you have to design your CMS to delay as much as possible your methane adsorption, what you're actually going to do also is you're going to delay your CO2 adsorption, and then your breakthrough curve will be more dispersed. So you are affecting the capacity of CO2 in terms of time, and you don't want to do that. So there should be a trade-off if you're designing the carbon molecular sieve where you are going to stop narrowing your pore. I hope that was a question.
Okay. Yeah, that makes sense. I think those are the questions. Thanks a lot, Professor Grande, for taking time to answer all of them. We really appreciate that.
So
Pleasure so much.
Thank you, Professor Grande, for your presentation, Pressure Swing Adsorption for Biogas Upgrading. We also thank all of our attendees for joining this webinar and hope it was both educational and enjoyable. An edited version of this webinar will be posted on the IAS YouTube channel and Bilibili with an announcement on the IAS Twitter feed. The hope is that the work discussed here today will be a useful resource for the adsorption science community in the future. With that, our next confirmed IAS webinar will be given by Yanwen Yang on July 31st at 8 a.m. UTC. Announcements regarding the next webinar and other IAS online events will be posted on our Twitter feed and through the IAS mailing list. With that, we thank you for joining us. I hope that you will join us again soon.